For today's webinar, we have Dr. Angie Christensen, a forensic anthropologist at the FBI Laboratory in Quantico, Virginia, and Dr. Mari Issa, an assistant professor of anthropology at Texas Tech University, presenting Forensic Fractography of Bone, a New Model for Skeletal Trauma Analysis. Today's Q&A session will be moderated by Michaela Askeles, a public health analyst in the Center for Forensic Sciences at RTI International. Without further delay, here's Angie and Mari.
Thank you very much for the introduction, and thank you to SOFA and FTCOE for hosting this webinar and inviting us to participate. During this webinar, we hope to introduce you to the science of fractography and explain how it can be used to interpret skeletal fractures. We're going to review some basic tools and equipment needed to apply forensic bone fractography, and hopefully demonstrate that with a little knowledge and practice, you can use fractography in your skeletal trauma analyses. This webinar will closely follow the content of this recently published guide. Hopefully you've had a chance to get a copy already, but if not, please download or request a copy at the end of this presentation. Fractography refers to the study of cracks and fractures in a material to understand the cause of its failure. And part of what we hope to convey and propose in this webinar is a bit of a shift from a more typological approach involving largely looking for documented patterns to something more akin to a failure analysis, where we ask, why and how did this bone fail? Fractography can be used to determine the point of origin of a fracture, identify the presence of flaws and localized stress concentration, identify material limitations, and reveal information about the microstructure and mechanical properties of the material. Fractography is frequently used in the failure analysis of engineered structures and products, often to ensure the reliability and safety of the materials. But it's also used in a variety of forensic investigations, including failure analysis of glass, ceramics, plastics, and metals. Pictured top left here is a window of a train that derailed. A circular fracture fueled speculation whether a projectile impacted the window prior to its derailment. But a fractography analysis showed that the window first failed when the cab impacted the ground on its side, and that the circular fracture occurred later. X-ray examination of this baseball bat revealed a crack as well as remnants of a previous repair. And as we'll learn in the rest of this presentation, fractography can also be applied in the analysis of bone fractures. Ultimately, fractography applied to skeletal trauma analysis can help provide a better understanding of bone trauma because it involves consideration of how and why the bone failed, not just the fracture pattern that resulted. Applying fractography to skeletal trauma analysis ideally includes a strong working knowledge of bone microstructure, mechanics, stress and strain, loading regimes, crack growth, and bone biomechanics. And we're not going to go into these concepts in detail here, but the guide does provide an overview, and we'll also provide some additional resources for further study at the end of the presentation. We'll start by looking at fracture origins. Identification of the fracture origin is often critical to understanding the cause of failure. Origins can be identified based on the shape of broken fragments, cracking and branching patterns, and features of the fracture surfaces. And this image depicts something interesting that I learned about glass fractures in researching fractography for this guide. Tempered glasses are manufactured to break into many small fragments when fractured. The two glass fragments adjacent to the fracture origin are typically polyhedrons with a greater number of sides than the other fragments and are also typically larger. This can make it easy for examiners to visually identify where the fracture started, even if the fragments are no longer together. The fracture origin refers to the point where a fracture begins, which will be at a localized flaw or weak point in a material. Irregularities in a material can act as strength-limiting flaws by becoming stress concentrators. These might include voids and cavities, inclusions, compositional irregularities, or micro damage. Pictured here left is a fractured ceramic bend bar, and a bend bar is just a manufactured piece of material used for bend testing, which measures the mechanical behavior of a material subjected to loading. In this bend bar, a spherical pore from a bubble in the material was the point of origin of the fracture. And pictured right, a low energy impact to a ceramic mug resulted in a crack that circumscribes the base of the mug. The fracture origin is near where the handle attaches to the base where there was a bubble in the ceramic. There were likely a variety of forces affecting the fracture initiation and travel, but tensile stresses were experienced at the handle base, and this bubble acted as a stress concentrator, causing fracture to initiate at the specific location. And here's a case example of a fractured tempered glass window. The window had only recently been installed, and it was initially speculated that it had been impacted by a BB or wind-driven debris. The origin could be located based on morphology of the adjacent fragments, similar to shown in the earlier slide. And between these two fragments is a small speck, which upon further examination was confirmed to be a nickel sulfide inclusion, which is known to cause spontaneous fracture in glass. A fracture will start where there is stress experienced by the material and a localized weak point within that stress zone. So the fracture origin will be the site with the most vulnerable combination of tensile stresses and flaw severity. In this long bone fracture, the arrow indicates where the fracture origin is. This doesn't necessarily mean that this is where the bone was impacted, but where it experienced the greatest tensile stress in combination with some weak point within that zone of tension. Fracture origins can result from a variety of different forces. Contact or impact between two objects can cause dynamic crack initiation and propagation. In forensic skeletal trauma analyses, fracture origins are often of interest in understanding where the bone was impacted. Impact sites may have localized damage or inclusions and may have associated fractures. Pictured left, a cranium experienced blunt trauma from a hammer impact, which caused localized damage. The fractures here are all within the immediate impact region. And right, there are multiple sharp traumas on this innominate caused by impact with a knife, some of which are indicated with black arrows. The one on the iliac crest caused tensile stresses in the bone, resulting in fracture initiation at the apex of the incision, and this fracture is indicated with the white arrow. Fractures don't always initiate in the immediate region of impact. They certainly can, but impacts impose stress distributions such that fractures can initiate in areas elsewhere on the structure. Bending forces, for example, can cause a crack to originate in a location remote from the impact site. This has been documented in numerous studies, including those involving bone. Pictured left, a femur broken in bending has a fracture origin on the side of the bone opposite the impacting object, since bending forces impose tensile stresses on the opposite side. This image also shows that the fracture origin is not directly opposite the impact site, indicating the location of a localized weak point in the bone in the zone of tension. The image on the right shows a remote fracture origin following a cranial impact. In this image, the fracture originates in the inferior temporal, near the arrow labeled A, and propagates toward the parietal impact site in the arrow labeled B. Due to the spherical structure of the cranium, impacts can produce deformations and tensile stresses in areas other than the impact site. In experiments involving impacts to the parietal, deformation and fractures were often produced in the adjacent temporal, which is mechanically weaker than the parietal. In bone, the opening of the nutrient foramen is a pore that can act as a stress concentrator. In a study of bones broken in 4-point bending, the nutrient foramen was found to correspond to the fracture origin in several cases. Other foramina in bones and even openings in cranial sutures may also act as stress concentrators, as can bone pathologies such as abscesses and cysts, or any change that causes a localized weakness. Once a fracture initiates, it extends and propagates under differential stress conditions, with the path depending on a number of intrinsic and extrinsic factors. At the origin, a crack will be straight and will propagate normal or perpendicular to the direction of maximum local principal tension. As the crack propagates, minor deviations in the direction of local principal tension modify the plane and direction of cracking. And if stresses are too great to be dissipated through a single crack, multiple cracks might be created. Fracture paths aren't random, but they reflect deviations and the need to dissipate stress. They can also provide information about the fracture origin and energy. Radial cracks from an impact originate from within the zone of contact and propagate outward, and these are often very easy to interpret. For example, the left image shows radial cracks in a fractured glass disc. The fracture origin is in the middle where the radial cracks meet. In the cranium on the right, radial cracks extend anterior and posterior from a projectile impact. If a structure is continually loaded, the radially fractured segments can bend inward, causing circumferential secondary cracking. This appears as roughly circular, semicircular, or arc-shaped cracks that are offset by the radial cracks, which came first. In these figures, you can see the initial radial cracks from the impact site and the arc-shaped cracks on the segments. As fracture speed increases from the origin, the crack may reach terminal velocity and split into two cracks, or branch, in order to dissipate the strain energy. Branching patterns can be an aid in determining the fracture origin. For example, a pair of branches in opposite directions typically bracket the fracture origin, as shown here in the top figure. And cracks will typically propagate normal or perpendicular to the original surface for a short period. So locating the fracture origin can often be accomplished by tracing the branching patterns back to the first normal fracture, as shown here on the bottom. Crack propagation and branching can also be affected as a crack moves from one type of stress field to another, for example, tensile to compressive, which may cause a sudden change in crack direction. There are often branching events associated with bones that fail in bending. Here, the dashed arrows indicate the fracture origin. The free fracture surface in each case is where a crack propagated through the bone thickness and vented at the bone's edge on the other side. But crack branching events were also experienced, indicated with the solid arrows, some of which did not propagate through the full thickness of the bone. The so-called butterfly or wedge fracture is an example of a crack branching pattern that has received considerable attention in the forensic literature. These will have a fracture propagating normal to the bone surface for a short distance before branching to form the wedge-shaped fragment. In these ribs that were fractured in a blast event, the initial normal crack prior to branching can be appreciated. The distance a crack travels before branching is related to the stresses and stored energy of the structure. The greater the stored energy, the shorter the distance before branching. The top two images in particular show differences in the crack lengths prior to branching, with the one on the left traveling only a very short distance prior to branching, while the one on the right travels a greater distance before branching. The initial crack in a structure will pass through the material undisturbed, perhaps branching. Assuming this crack completely cleaves the material, a second crack that intersects this first crack will stop, since the energy will be dissipated through this discontinuity. This can be useful in determining the sequence of cracks associated with a trauma event. Here, the cracks indicated with white arrows preceded those indicated by the black arrows, as evidenced by their termination into the first cracks. In the cranium, fractures may initiate from sutures, which can act as stress concentrators, and can also terminate into cranial sutures, which dissipate the fracture energy, similar to a pre-existing fracture. In this experimentally generated cranial fracture from an impact, the fracture terminated at the white arrow in the sphenoesquamosal suture. Because cracks branch to dissipate energy, higher energy impacts cause a greater number of branching events and therefore produce a greater number of fragments. This extensive fragmentation is often referred to as comminution in forensic anthropology. In the two experimental examples pictured here, there was a greater transfer of energy in the impact on the right, resulting in the need for increased branching to dissipate the energy, and therefore a more comminuted fragmentation pattern. And this case example involved a high energy impact resulting in many cracking and branching events and significant comminution. Impacts or contact loadings can also produce something called a cone crack, which is a conoidal fracture that results when an object passes through or impacts a brittle material. Propagation of a cone crack through a structure results in the formation of a cone-shaped piece of material and leaves behind a cone-shaped void. The conoidal morphology of the void created is commonly referred to as beveling in forensic contexts, and its production has been attributed to a variety of mechanisms. But cone cracking is well understood to be the mechanism responsible for bevel production in other brittle materials such as glass. And pictured on the right here is a car passenger side window that was discovered on the side of the road following a shooting event in which a victim in the driver's seat was found with gunshot wounds. The fragments here are held together by an aftermarket tint that was applied to the inside of the window. The morphology of the cone crack in this case indicated that it initiated on the tint side of the window, and therefore that the projectile that caused it came from inside the vehicle. Cone cracking has also been shown to be the mechanism responsible for this pattern in bone, and has also been found to be associated with low velocity projectiles and even blunt impacts. A schematic of cone crack formation is shown here on the right. When an applied load reaches a critical value, a ring crack forms due to tensile stresses on the impacted surface of the structure. This ring crack will be concentric with and just outside of the area of the two contacting bodies, which is where the tensile stresses are greatest. The initial ring crack propagates normal to the free surface of the structure for a short distance. With increasing load and shear forces, the crack will propagate outward. This outwardly propagating crack is the cone crack or bevel. Pictured here left is an incomplete cone crack in a bone examined using micro-CT. The top portion shows the ring crack that formed on the impacted side of the bone. On the bottom is a cross-sectional view of the same fracture showing the ring crack and the initial flaring of the cone crack, which did not travel all the way through the bone. The right images show a complete cone crack in a bone. The top image shows the side of projectile exit, with most of the conoid fragments still in place. The bottom is a cross-sectional micro-CT view of the same cone crack, which shows the line of the bevel, as well as the in-place conoid fragments. Intersecting cracks can be used to differentiate between circumferential and cone cracks based on whether the curved or linear cracks are continuous versus terminating into previous cracks. In the case of circumferential cracks from inward bending, the radial cracks appear first and will be continuous, while the circumferential cracks, which appear later, will terminate into the radial cracks and be discontinuous. So on the left here, the solid radial cracks came first, and the dashed circumferential cracks came after. In the case of ring and cone cracking, which is pictured on the right, the ring crack appears first and will be continuous, shown with the solid line, while the radial cracks, which appear later and are shown with dashed lines, will be discontinuous and terminate into the ring crack. So I'll give you a moment here to examine this crack pattern on a cranium. What type of cracking is this? Is this an example of secondary circumferential cracking or cone cracking? Which came first, the circular crack or the linear radial cracks? In this case, the circular fracture came first, and this is a cone cracking event. The circular crack is continuous and therefore occurred first, and the discontinuous radial cracks came after. This is also an example of a cone crack resulting from a low velocity impact. The conoid here is large, and the cracks within the ring represent comminution of the conoid. And here are three additional examples of cone cracking from low velocity blunt impacts. The top one from a case and the two bottom ones from experimental impacts. In all three cases, the ring cracks are continuous and the ring defect is internally beveled. And I'll now turn it over to Mari to discuss the next couple of sections.
Thank you, Angie. So in this section, we'll be discussing fracture surface features. And a fracture surface is a surface that's created by the separation of two parts of a material as a result of a propagating crack front. We'll start by discussing fracture surface features in glass and ceramics before moving on to bone. Fracture surface features are related to the origin as well as the speed and stability of a propagating crack. They can reveal information about the mechanical properties of a material, as well as the mechanism of failure, the location of fracture initiation, and the direction of crack propagation. Glass is a useful introductory example when learning about fracture surface features. And this is because glass has a fine microstructure that shows many fracture surface features very well. 3 well-documented and easily identifiable features in glass are the mirror, mist, and hackle regions. As a propagating crack front expands from the origin, the speed of the fracture will rapidly increase. The region that's closest to the origin is often associated with a smooth, featureless region called the mirror zone. The mirror zone surrounds and is centered on the origin. Just outside the mirror zone, there is a mist region, which marks where local deviations from the main fracture plane first become optically discernible. And as the crack advances, these deviations increase and form larger rough steps that are referred to as hackle. These features can also be seen in more structurally complex materials such as ceramics. However, they might appear differently due to these materials' larger microstructure. For example, the mirror zone in ceramic is less smooth than it is in glass, and hackle tends to be more rounded. Wallner lines, which are also called rib marks, are curved lines on a crack surface that are concave in the direction that the crack is propagating. The image on the top left here shows an example of Wallner lines on a ceramic fracture surface. The direction of crack propagation is shown with the solid white arrow, and the dashed line highlights a Wallner line. Wallner lines result from the intersection of the expanding crack front and an expanding elastic wave, which cause the crack to ripple out of plane, kind of like a wave on a pond surface. Twist hackle is another fracture surface feature, and it's shown here on the top right in a glass example. Twist hackle results as a crack passes a microstructural feature that causes localized lateral rotation of part of the crack away from the main direction of crack propagation. And arrest lines, which are pictured here on the bottom, are sharp lines on a fracture surface that results as a crack is arrested or momentarily hesitated. The arrest line occurs as a crack progresses along a slightly different plane, usually in response to a slight change in the axis of principal tension. Arrest lines can be curved or straight, and they are sharper than Wallner lines, which can help in their differentiation. In this case, the arrest lines resulted from cyclical loading of a glass plate. Some other surface features that you may encounter include wake hackle and cantilever curl. Wake hackle is a linear feature that results from a split crack front that passes an obstacle, such as an inclusion or a pore. As the propagating crack front reaches the other side of the inclusion, the angle will shift slightly and create a mark that's aligned in the direction of the crack propagation. On the image on the left, we can see a fractured glass surface. The dashed arrow shows the direction of the crack propagation, and you can see several bubbles in the glass, as well as the wake hackle marks, which appear on the following side of those bubbles. The solid arrow marks just one example of wake hackle in this image. Cantilever curl is a curved lip on a fracture surface that occurs just at the fracture terminus. The image on the right shows a glass rod that was broken in bending. The dashed arrow here shows the direction of crack propagation, and the solid arrow shows that lip that is the cantilever curl at the very end of the cracking event. It's important to note that while the terminology that's used to describe fracture surface features is somewhat standard, it does vary somewhat between different materials because of the differences in the appearance of those features. It was necessary to develop terminology specific to bone because features appear somewhat differently in bone than it does in other materials, both in the quality as well as the degree of expression. In the next couple slides, we'll further describe some of those bone surface features here. Bone mirror is a region that occurs at a fracture origin, and it's relatively flat compared to the rest of a fracture surface. Bone mirror is never going to be as flat or as smooth as it is in glass, and it may not even be detectable in some cases because bone is highly porous and has a large microstructure that may obscure this feature. But bone mirror can be identified as the most featureless portion of a fracture surface. The bone mirror in these images is shown in brackets, and the direction of crack propagation is shown with a dashed arrow. Bone hackle is coarse in appearance, and its edges tend to be rounded, more similar to how hackle appears in ceramics than it does in glass. These rounded ridges will be aligned in the direction of crack propagation. Again, the solid arrows here highlight the bone hackle, and the dashed arrow highlights the direction of crack propagation. Twist hackle is a bit more difficult to detect in bone, but it can be found, and it would be seen as a series of roughly parallel ridges that radiate at an angle to the main crack front. These ridges will point in the direction of the localized crack propagation. In coarse-grained materials like ceramic and bone, twist hackle marks might not all line up in the same way, and this is because the crack is detouring through the bone microstructure in response to local features as well as local stress conditions. With glass and ceramics, we discussed arrest lines. However, in bone, this feature will look a bit different. Arrest ridges often appear very prominently on bone fracture surfaces. In bone that fails in bending, there's not a distinct halt in crack propagation. However, as the crack reaches the compressive side of a bending fracture, there will be drastic changes in the velocity of the crack propagation. The cracks will slow down very rapidly once they reach the compressively loaded part of a bone. And this will result in pronounced ridges or peaks that are referred to in bone as arrest ridges rather than arrest lines. Arrest ridges will be aligned approximately perpendicular to the direction of crack propagation. Like in glass and ceramics, when a crack front propagates around a small inclusion or pore in bone, wake hackle can be seen as a singular line that extends from the following side of the pore. Again, this is caused because a crack front is splitting and the two sides of the crack wave become slightly out of sync as they pass around the pore. Tubular bones that are broken in bending present an interesting condition where a crack front is propagating not around a small pore, but actually a very large inclusion, the medullary cavity. At the same time, the force is changing from tension to compression. So rather than splitting around a small singularity, all the surface features of the two sides of the out-of-sync crack wave become offset. And this is most notable in the arrest ridges. In the image here in the center, the oval shows an example of where the arrest ridges are not continuous across the surface of the bone and in fact are offset. This configuration where the features on the two sides of the crack front are out of sync is called a wake feature. And finally, cantilever curl is found on the compressive side of a bone that's broken in bending, and it represents the final feature in a fracture event. It's often the most easily identified fracture surface feature, and sometimes the only identifiable fracture surface feature in bone. If there is branching that's associated with a fracture, there may be two or more cantilever curls present in the same element. It's important to note that fracture surface features indicate the direction of crack propagation, but this is not the same as the direction of the applied force, and in fact may be directly opposite the direction of applied force. Many bones, especially tubular bones of the limbs, fail in bending. A force will be applied to one side of the bone, which causes the bone to fail in tension on the opposite side. The crack then propagates back towards the side of force application. So fracture surface features in themselves are not sufficient for determining the direction in which force was applied. Additional information about the fracture may be needed either from fracture patterns or from other bony or contextual evidence. In this section, we'll be discussing some of the tools and equipment that can be useful in fractography analyses. The great thing about this is that many of the tools and equipment are relatively easy to access and inexpensive. Many features of interest in a fractographic analysis are visible with the unaided eye, but depending on what detail of examination is needed, or perhaps the size of the specimen under examination, it may be helpful to use greater magnification or other visualization aids. It is always recommended to begin with unaided visual examination of a bone, and this will include examining each broken piece, the overall cracking and breakage pattern, as well as all of the fracture surfaces. This initial visual examination is important because it allows you to become acquainted with the overall pattern as well as orient the components. Low power magnifiers can be really useful in these early stages of analysis, and most of them are fairly inexpensive and offer a lot of flexibility. Handheld magnifiers, such as a magnifying glass, can offer anywhere between 2 and 6 times magnification. The image shown on the slide here is a loop, which is an instrument that's held up to the eye, or in some cases held within the eye's socket. Loops are used by biologists, geologists, and jewelers to examine small objects and typically offer from around 10 to 20 times magnification. Microscopes can offer even higher magnification. Pictured on the top row here from left to right are examples of stereo microscopy, compound microscopy, and scanning electron microscopy, or SEM. Most features that are of interest in forensic fractography of bone are not going to require the need for magnification greater than you can achieve with stereo microscopes. These instruments are luckily also among the least expensive and easiest to use. When examining specimens under stereo microscopes, it can be particularly useful to use a specimen holder during analysis. Many practitioners are familiar with large specimen holders such as cork rings, beanbags, or sandboxes. But to position bone fragments for surface examination, a small piece of polymer clay can be used to position the element so that the fracture surface is in the position that you need it. An example of this is shown at the bottom of the slide. Note that polymer clays are recommended over conventional sculpting clays because sculpting clays can blend into fracture surfaces and can be difficult to remove. Polymer clays can be removed more easily, and anything that adheres stubbornly can be removed with acetone or ethanol. The use of contrast media can help to accentuate features or increase observable detail, and this can be useful for visual examination as well as photography and microscopy. Inks and dyes can be particularly useful when visualizing incomplete or very small cracks. In ceramics, dye penetration is often used to search for hidden cracks. The same approach can be applied to bone. The images on this slide show the same bone specimen before and after the application of ink. Ink was applied using a small paintbrush to the fractured area, and then a wet paper towel was used to quickly wipe away excess ink to avoid staining the surfaces. This was repeated along the fracture until all of the hairline cracks were highlighted. The result is a very clear picture of many small cracks that were not previously visible visually and certainly not in the photographs. It's important to note that generally reversible coatings are recommended. However, the application of dye or ink in this way should be considered permanent when applied to bone because it can be difficult to remove ink from those hairline cracks. Another type of contrast media that's available are surface coatings. Coating fracture surfaces can also help to accentuate details by decreasing the reflection and increasing the contrast. The images on the top here from left to right show bone cast replicas that have been treated in different ways. On the far left, we have an uncoated specimen, and then the next 4 specimens have been coated in order with black fingerprint powder, dual contrast fingerprint powder, silver ink, and gold sputter. The dual contrast fingerprint powder was found to best enhance the surface details. This was even better than the black fingerprint powder because the black fingerprint powder had a mattifying effect that reduced contrast. Fingerprint powders are convenient because they are reversible as well as inexpensive. Fingerprint powders were used in the case analysis in the bottom two images, which involved a 6-year-old who was struck and killed by a car. In this case, analysis of the fracture surfaces confirmed the direction of crack propagation and impact, which corresponded to soft tissue findings at autopsy. The source and the angle of illumination is also an important consideration in fractography analysis. Oblique or low angle illumination is particularly useful for bringing out features on fracture surfaces. This can be achieved using various sources, including gooseneck fiber optic lights, such as pictured in the left of this slide. However, light rings, small flashlights, and even cell phone flashlights can be used as light sources. The impact of oblique lighting is illustrated in these images on the right. We have 4 examples here of the same fracture surface. The left 2 images are not treated with fingerprint powder, while the right 2 images have been treated with fingerprint powder. The bottom images show the same fracture surfaces with oblique lighting applied, and you can see how the oblique lighting really highlights the fracture surface features. While observing bone surfaces with oblique lighting, it is important to completely rotate a specimen while adjusting the illumination source because light will bring out different features better from different angles. Sketches are important in the documentation as well as the interpretation of fractures. Experienced fractographers will advocate for using sketches rather than photography alone because sketching requires an analyst to interpret a fracture pattern as they are reproducing it in a sketch. These are 2 examples of bone fractures that have been supplemented with sketches. On the left, we have a sketch that has been generated using computer software, and one on the right where the sketches have been hand-drawn. In both cases, the fracture patterns are greatly clarified through sketching, and particularly some of those hairline fractures, which are more visible in the sketches than in the photographs. As with any skeletal trauma analysis, fractography should be amply documented with photographs. And ideally, this will involve overall images as well as some more detailed and even annotated close-up images of features of interest. In the images on this slide here, the top image shows a femur that has been fractured, and the bone fragments have been arranged in approximate anatomic position in this image here. In the bottom left image, we see a close-up of one of the fracture surfaces of the distal fragment here. And then in the 2 images on the right, we see microscopic views with the bone mirror and cantilever curl highlighted. In fractography analysis, it can be useful to communicate simultaneously the overall image with some of the smaller, more close-up images that are produced as part of the documentation. Something that's useful in this process is the creation of a fracture map. A fracture map is a montage that's composed of local images that show smaller fracture details that are organized systematically around an overall image. Overall images are important for orienting viewers and showing larger patterns of fracture, but they're not able to communicate those smaller features effectively. So a fracture map is useful in that it helps connect this local information with a global interpretation. Here, the overall image is shown in the center. Some of the close-up images are shown surrounding it with the fracture surface features annotated and interpretations about crack propagation direction as well. Other photography approaches also have potential utility in bone fractography. For example, photogrammetry is shown in the image on the left here. Photogrammetry uses a series of photographs that are taken from different angles to create a 3D model of the object being photographed. On the images on the right, we see an example of reflectance transformation imaging, or RTI. RTI combines a series of variably lighted photographs to create an interactive digital image where surface details can be enhanced using software adjustments. Radiology is also quite useful in fractography analysis. It's a non-destructive, non-invasive method of examining internal structures of bone that can also be used to detect and analyze fractures. CT scanning and other 3D radiologic imaging approaches can be particularly useful in examining fractures as well as bone fracture surfaces. Micro-CT scanning, which is pictured on the top left here, captures a significant amount of surface detail. But even with traditional medical CT scanners, it's possible to capture features such as arrest ridges and cantilever curl very well. This case shown here involved an individual who was in a motor vehicle accident that resulted in a femur fracture. The orientation of the fracture surface features allowed for a clear interpretation of crack propagation direction, which is shown here with the dashed arrow. Replication of bones or parts of bones can also be useful in fractography analysis. For example, it might be impossible or impractical to examine the fracture surfaces of very large or very long bones under a microscope. In this case, a low-profile replica can be created as a way of examining a small area of a larger piece. One option is to create a cast replica. This process requires multiple steps. First, a negative mold must be made, but then once that mold is created, it can be used to make multiple positive replicas. This can be beneficial for research as well as other testing, especially testing that would require non-reversible treatments. For example, gold sputter for scanning electron microscopy. In the left image, a mold of a femur fracture surface was created using silicone, and then a replica was made with resin. If you have access to this technology, replicas can also be made digitally using CT or surface scanning. Pictured right on the top is a bone that was scanned using micro-CT. These images can be manipulated and analyzed digitally using computer software, and they can even be used as the basis for creating 3D prints as pictured below. And finally, reconstructing fractured bones can clarify branching and cracking patterns and can help understand the relationship between fragments. In this case, the cranial vault was received as 13 separate fragments, but there wasn't a clear picture of the fracture event. After reconstruction, however, a cone crack, radial cracks, and circumferential cracks all became quite apparent. While it may be tempting to immediately refit bone fragments into their anatomical positions, reconstruction should really only be performed when necessary to gain additional information. This is because attempts to refit fragments may actually alter the surfaces through abrasion or chipping, and this could mask or obliterate surface features that would be important to the analysis. If performed, reversible reconstruction methods should be used to allow for the later analysis of fracture surfaces. I'll turn it over here back to Angie to finish this presentation.
Okay. We're getting a better understanding of how fractography can be used to understand bone failure, but there's so much still to be learned. In the guide, we suggest a number of areas that we think would benefit from additional study, including laboratory loading tests and fractography of non-blunt and non-impact fractures, for example, sharp and thermal fractures. Much more could also be investigated in areas such as the relationship between force and crack lengths, branching distances and angles, and cone crack geometry in bone. As with anything, the more fractography you do, the easier it will become. Self-guided and hands-on experience are really valuable, and we highly recommend it. Look at as many fractured specimens as possible. This could be fractured human bone, non-human bone, or really any fractured brittle material. So the next time you encounter some sort of fractured material, conduct your own failure analysis. See if you can find the flaws, locate the fracture origin, and determine the direction of crack propagation. There are also a number of great resources out there to help. In addition to the Bone Fractography Guide, the NIST Recommended Practice Guide for Fractography of Ceramics and Glasses is an excellent resource, and I would suggest should be read by any anthropologist planning to do fractography on bone. So to conclude, we hope we've shown you that fractography can be a really informative addition to your skeletal trauma analysis cases, and that you can apply it using some fairly basic tools, equipment, and techniques. And finally, we hope that we have convinced you that with a little knowledge and practice, you can easily and effectively apply this approach in your casework. And we would like to acknowledge the other co-authors of the Fractography Guide. Neither the guide nor this webinar could have happened without their contributions, so thank you. And these are citations for materials and images used in this presentation. And contact information for both presenters. Please do not hesitate to reach out to us directly with any questions. And we are available for questions now, and you may put any questions that you have in the Q&A pod. Thank you.
Hi, everyone. My name is Michaela Askeles, and I'm a public health analyst at RTI International and their Center for Forensic Sciences. And I'm going to be your moderator today. Thank you so much, Dr. Christensen and Dr. Issa, for providing such an informative presentation. If you have not already, all attendees, feel free to just pop any questions in that Q&A pod. All right, so our first question is about, could a fracture of a rib help determine if the victim of a shooting was in standing or a horizontal position?
I'll try to field that. I'm not really sure because this is really more about how the bone failed. So unless I'm trying to imagine a circumstance in which the bone would fail differently from force in one position versus another, I'm not sure that this would be the approach necessarily to answer that question.
Okay. Yeah, if they're if the person who put that question in, if they want to clarify anything or they have any further questions, yeah, feel free to add to that question. All right. Another question we have is, in theory, could you receive a cantilever curl on the curved spur resulting from sawing? I know this is another specific example.
I can take this one. In case you're not familiar, when a bone is sawed, a lot of times that final failure will not be because you've cut through the bone, but instead because the bone is breaking and bending at the end. And so yes, a cantilever curl could be observed on that end of that saw mark.
All right, thanks for answering that. See. Next question is, how are the observed bone fracture features affected by the surrounding tissues, and are ante, peri, and post-mortem short-term and skeletonized injuries able to be differentiated?
Okay, I'll address that. So as you saw from the CT scan, you do see these features in bone from living tissue. So that was an accident injury or an accident victim CT scan. So you can still see those features, though the resolution is somewhat less than looking at them directly. In terms of whether it's perimortem or postmortem, the differences you might see would reflect the fact that as bone dries, it's becoming more brittle. So in theory, these features would become more pronounced. There actually have been a couple of studies where people have looked at bone surface morphology in perimortem and postmortem bone. And what you are seeing is a reflection of the fact that as it dries, the bone becomes more brittle and it therefore acts more like a ceramic or glass.
All right, and then the next question is pretty straightforward, but someone's asking if you have a recommended type of brand or type of ink or dye that you use.
I can take this one. One of my former graduate students had done a little bit of work on animal bone. That's where that image from this presentation came from, trying to see what kind of inks might work. And so a couple of them were tried. The ones that she had the best success with were specifically Dale Rowney black acrylic ink, and I can later on type that into the chat if that's helpful. As well as she also tried Hampton Art Ultra Washable Blank Ink Pad, which is really just kind of a crafting type of pad. I'm not sure that I would recommend any particular types of inks though, because we were not able to fully remove any of them. So that's something to consider if you are going to try that. However, some sort of liquid acrylic ink was usually the most easy to apply. Getting the bone a little bit wet first, then dripping a little on, and then wiping the excess off was the most successful technique.
Oh, sorry. And just a follow-up of that. So did you have any recommendations? Did that student, is that just the type of ink or dye you had on hand at the time, or did you all have specific recommendations that you received leading you to use those?
Sure. We did not have any specific recommendations for use of inks on bone. These were selected primarily just based on cost and wanting to try a couple of different options. So she tried things that were applied with a pen, more liquid inks, as well as stamp pads to see if there was a difference in the way that the ink was applied, as well as I think that she also tried to choose the reason for some of the crafting inks was because sometimes those are marketed as washable. So she wanted to see if those would be removed easily. And unfortunately, none of them were.
Okay.
And just a quick add-on, I don't remember what type of ink they use, but if you look at the glass and ceramic guide, George Quinn does recommend certain inks for use on ceramic. I'm not sure if those same inks would be recommended for bone or the reason for recommending those specific ones, but that guide may have some additional information.
Okay, great. All right, and then we have another question. So this person saying, I'm coming from a failure analysis and I'm more familiar with ceramic and metal fracture than bone. Could you comment a little more on the flaws and/or features that commonly initiate cracks in bone?
I can try to take that. The short answer is there's a lot we don't know, but pretty much any weakness in the bone. So this could be a pore, an infection, anything that's going to cause a localized weakness is going to concentrate the stress in that area. But this is another one of those areas that would be great for additional research.
All right. Do you know anyone doing additional research in that yet, or it's still pretty unknown? Okay. All right, the next question is fractology. Is fractology giving us more details about the cause of death? I know that's very general.
I'll try to take that, and I'm going to say I don't think so, because ultimately, using this approach, anthropological findings in theory should be still just documenting the skeletal trauma patterns. So they're about understanding how and why the bone failed, but I'm not sure that that's necessarily directly correlated to cause of death. And I think anthropologists should still be cautious in just reporting what they're seeing in terms of the bone failure.
I see. All right, great. And then we have a question. Can you speak to fractures that propagate through sutures instead of terminating in them? Are there certain patterns?
I can start, and then I'm sure Angie also probably has something to add here because I know you're interested in this question as well. I've done some experimental research on cranial trauma, and what we were seeing is it seemed like primarily fractures are either propagating from sutures or terminating at sutures. They're only really crossing them if there's some degree of closure in the sutures, if those have begun to fuse. Did you have something that you would like to add though, Angie?
Yeah, sure. So I think I think there's some question about whether cracks actually do cross sutures, and maybe they appear to, but in some cases, what I've seen is what appears to be crossing a suture is either, like Mari just kind of suggested, that there was already some degree of closure there, so there was a pathway for the crack to cross, or a jog in that crossing where actually what was happening is either two different fractures terminating into it or originating from it, or one of each, but not actually the same crack propagating through that opening.
Gotcha. And then another question, how reliable is fractology for buried skeletons? Have you had any cases like that you've worked on or know anything?
I'm not sure that burial would necessarily affect the ability to apply fractography. Again, the drier the bone becomes, the more brittle it will be. And in theory, the more pronounced those will be, the features might be, but I'm not sure that burial really would have any impact. Certainly taphonomic activities could alter the appearance of fractures or bone surfaces, but that's the case for any analysis of remains that have been buried long term. But I'm not sure that the burial process itself would affect the ability to apply this.
Okay, so you said, the drier the bone and the better it is for analysis. So I guess if the bone has more moisture, it makes it more difficult. Let's say during the burial, moisture got into the bone.
No, it's more that the fresher the bone is, the more ductile it is. Okay. So the drier bone becomes, the more it acts and fails more like a brittle material like glass and ceramic. So it's not, if I misspoke or was misunderstood, it's not that it's better, it's that in theory, so Mari talked about how these features are very visible on glass because glass is a non-porous, very smooth, very small microstructure material. Bone is never going to be like glass, but the drier it becomes, the more it behaves more like a glass or ceramic. So those features might become more visible or be more pronounced.
I see. All right, great. All right, we have another question about if fractures of bone in the forehead are caused by a heavy dumbbell at a gym, then how would that be analyzed?
I think, oh, sorry.
No, go ahead, please.
Well, I think the great thing about fractography is it's not necessarily specific to any particular cause of skeletal trauma. So just in the same way that you would apply fractography to really any skeletal analysis. Did you want to jump in there, Angie?
I mean, is the question about, whether, because this impacted somebody who is still living, or, I mean, I assume that the fractures are going to be like any sort of blunt impact, but studies using CT scanning have shown that you can apply fractography even to living tissues by CT examination.
Yeah, whoever put that question in the Q&A pod, hopefully that was answered, but if you do have any more clarifications, feel free to add. We'll just go ahead and move on to the next question though. So the next question is the rest of anthropology embracing this fractography terminology? Is the breakaway spur the same thing as a cantilever curve?
I can take this. Actually, Mari already answered the first one with the previous question. The cantilever curl or the breakaway spur that you're seeing is not from cutting, but from the bone actually breaking at the end. In terms of the first part of that question, sorry, can you just repeat it for me? I got sidetracked by answering the second part first.
Yeah, it's just asking if, the rest of the anthropology field is embracing this terminology with fractography.
I am certainly seeing more publications that are addressing bone fractography. So I'd like to say at least among some of the younger researchers, I think that is the case. We worked with Hugh Berryman and a number of other experienced anthropologists and fractographers on the guide. So I do think people are coming around to it. I know that it's kind of new and it might take people a little time to warm up to it, but people do seem to be getting on board.
Yeah, and kind of a follow-up of that. So when you're applying that fractography in like the report results, are you using that same language when you're reporting, or you're making it more specific to bone in that trauma analysis?
I can talk about my reporting, and then Mari, if you want to as well. It's not really affecting the reporting. I mean, we're still, at least at my agency, using OSAC and proposed, or SWIGANTH and proposed OSAC guidelines in our reporting and skeletal trauma analyses. This is more about the practitioner having a better understanding of what happened and what caused those fractures by trying to understand where the fracture started, how it happened, and how that crack propagated, rather than just looking at the end result and trying to categorize it into one of a few categories.
No, that's great. Yeah. Another question, do you consider that the pattern of fracture and repeated contusions produced by a projectile fired at by a high-powered firearm repeats its behavior?
So, we would certainly expect that once a bone is already fractured, that any subsequent impacts would behave differently than if that structure had previously been intact. We talked a little bit about intersecting cracks, places where fractures will typically be arrested. Also, the presence of a fracture or fractured structures will create flaws from which fractures might also begin. Did you want to add anything, Angie?
No, I think that's exactly right. I mean, as soon as you've impacted it and caused these fractures or branching or whatever, you've kind of changed the structure. So any subsequent impact is going to, but the bone is still going to fail in predictable ways, but you've introduced a bit more discontinuities and things in the bone prior to that second impact.
Great. All right, next question. Since collagen affects how ductile bone is, would collagen affecting life events such as chemotherapy be expected to change the appearance or prevalence of fractographic characteristics in an individual?
Well, the short answer is, again, maybe this is an area that would be good for research because I don't necessarily know the answer to that. And even though we've talked about it, and I've said several times now that bone is going to become more brittle as it dries and behave more like a more brittle material. My guess is that those differences are still going to be rather subtle, and that the differences in bones' biomechanical properties aren't going to really drastically change based on the collagen content or the brittleness of the bone. But that sounds like an area that could use more study.
All right. I know we were kind of talking about burials earlier, but we have a question about in commingled skeletonized remains recovered in a burial context, can knowledge of fractography help reconstruct fractured/fragmented remains to better estimate the minimum number of individuals?
Do you want to take it, Mari, since you talked about reconstruction?
Sure. I'm trying to think about this. I guess I really haven't thought about the application of fractography to this particular question. I suppose if you are familiar with what the different fragmented pieces are that you're looking at, perhaps that would help you locate potential matches. Overall, though, I imagine that it would really be more about overall, identification of the element first and the location on that element, and then probably you would just need to refit them. I'm not totally sure how fractography might apply to this question. Do you have any ideas, Angie?
Yeah, kind of the same. I mean, reconstructing to the elements to estimate MNI from commingled remains is really going to be more of an osteology problem, and getting those fragments back into their anatomical positions. So fractography is going to be more about understanding why were those fragments separated in the first place? How did the fractures occur? Not necessarily the putting them back together.
Yeah, that's good to know. I think it's also, I'm sure, important to take into context whether those fractures obviously occurred, during the individual's lifetime or before burial, post-mortem, etc. All right, we have another question. In terms of living tissue analyzed by CT with woven bone and bone healing processes, has this effect to the bone fracture surface been analyzed? In the case of a death happening before healing is complete, can these analyses be applied?
I haven't personally analyzed or seen a case like that, so I don't know. My guess is that the bone will be weakened there, so that might be a point of stress concentration and act as a place where a fracture might initiate, but I'm otherwise unfamiliar because I haven't analyzed a case like that.
And then Mari, did you have anything to add or any experiences?
I don't have any experience analyzing a case like that. Perhaps if I'm interpreting this question to mean if someone sustained a fracture shortly before death and there was maybe some degree of healing, would some of those features be visible on CT? It's possible in the early stages. It does take bone a while to heal, but I don't have any knowledge of that. I haven't seen any cases like that.
Okay. And again, we touched on this earlier in regards to buried skeletons, but we have a question on whether can the abrasiveness of the soil and minerals in dirt alter the fractures seen?
This actually is a pretty relevant question because it impacts how the fracture surfaces might appear. And in fact, experienced fractographers and other materials will often recommend not trying to refit fragments because of the potential to alter or damage those fracture surfaces. So yes, I mean, I think abrasive materials could alter the surface, which might make them more difficult to interpret. But this is actually one area that we recommend for future research in the guide, because we don't really know how trying to refit fragments or other types of taponomic processes might affect the appearance of the surface features. That's a good question.
All right. And then one more question. Fractography helps establish the order of events at a crime scene, amount of force applied, and in some cases, direction of impact. I guess they're asking, does fractography help establish that, the order of events?
So I think to clarify, it is looking at allowing us to reconstruct the type of force applied, hopefully the amount of force and potentially the direction of impact, but it's really about establishing how the bone broke and then why. In terms of order of events, not so much the crime scene, but more so if you do have, for example, multiple impacts to the same element, then reconstructing some of these questions, how did the bone break and why and where, might help you determine the order in which those events occurred.
Great. So again, if anyone else has further questions, feel free to just put it in that Q&A pod. You've already talked a little bit about the guide. And I know you in your presentation, you noted that anyone here can download a copy of that. Is there a cost to that? Will there a link that can be sent out?
I believe there was a link for the presentation on your website, but for anybody who wants a copy of the guide, it is available free online as a downloadable PDF through Zenodo. If you would like a hard copy, just email me with your mailing address and phone number, and I will send you a copy. And the hard copy is also free of charge.
Great, that's wonderful. And they actually just put a link to the guide in the chat as well for everyone.
Thank you.
Let's see. I don't know if this was touched on, but could you elaborate more on how you create your fracture maps?
Sure. Yeah, so the key with the fracture maps is that you need an overall photo and then you need those close-ups. So one step in that process is actually getting those images. And through that process, it's helpful to keep track of which fragment that you're looking at, especially when you're taking those close-up photos. I like to temporarily label with pencil or just using paper and kind of laying out the fragments on that paper and labeling it to keep track of which fragments I'm photographing. I actually use Adobe Illustrator. You could probably use Photoshop as well. And it's just a matter of arranging those different photos around the overall image and then labeling them. I think that the labeling is very important to make sure that you stay oriented. If I know that Photoshop and Illustrator you do pay for, I think you could probably make a reasonable version on PowerPoint if you really were in a pinch and you didn't have any of the Adobe software as well.
Great, yeah. And then for your photography, is there a certain camera that you use or any equipment on that end?
Really just, I take my photographs with a copy stand and a digital camera. I have an Nikon and I take all the photos against a black background, pretty standard forensic anthropology photography. I do also like to use a stereo microscope and an attached camera to take some of the closer photos. But for the most part, the fracture maps, I believe all of the ones in this presentation were just done using a regular digital camera, no fancy attachments or anything.
Okay, that's awesome. All right, looks like we have a couple more questions. Someone You mentioned before the potential for soil and taphonomic processes to alter the appearances of these features. Would the cleaning process of bone also affect that if you were to clean the bone?
Potentially, again, I guess depending on how you're cleaning the bone, this is something, as I mentioned, that we've suggested as an area of future research in the guide, because we're not really sure how a lot of these processes will affect these smaller surface features.
Okay.
I will add that there's been some research that indicates that processing may affect cut marks and some of the sharp force evidence, but we don't know how that might affect some other types of fractures.
Yeah, hopefully more research, will come about. One more question. If the fractured bone is underwater, will water currents have the same effect on bone as it does on rock?
I think that'll be similar to, soil or contact with any other medium in the taphonomic environment. Anything that is abrasive or in contact with, or even just affecting, even being out in the sun or exposed to the elements can potentially affect the bone surfaces.
And then another question, environmental question, but is there a difference between fractures due to burning and other fractures?
The short answer is yes. The long answer is we really don't know much about them. So thermal fractures in other brittle materials are very low energy fractures. So it's suspected that in thermal fractures, you probably won't see features like a lot of the surface features because the crack is going to be moving very slowly. But this is another area that we recommend in the guide for future research. It's something that I'm personally very interested in. So I may beat you to it if I find the time, but I think looking at thermal fractures using fractography is an area that really needs more study, and it would be really exciting.
Great. Oh, and we have some more questions rolling in. One more question. Sometimes engineers use dye penetration to see how deep a stable, unseparated crack goes. They apply dye, then fracture the part the rest of the way. The dye helps see where the original crack was. Is this something that can be useful for a bone?
Mari, do you want to try and take that one?
Sure, I'm trying to understand the question.
Yeah, I can read it again.
I think what this might mean is in some engineering studies, they'll actually kind of initiate a small crack and then see how that continues to go. And I'm guessing what they mean is after that they initiate that crack, they'll apply dye and then fracture the material the rest of the way. Potentially that could be useful for bone. I don't know of many studies, particularly ones that are primarily focused on trauma, skeletal trauma, that have taken this approach. If there were studies that were looking more at the material properties of bone, this might be something that's useful though. It's the difference is really understanding how fracture propagates through a material once the crack is already initiated, versus a lot of times, especially in the forensic anthropology context, experiments are being conducted to see how a intact bone is going to fracture in response to dynamic forces rather than static forces.
All right, thank you. All right, I don't see any more questions in the Q&A pod. I guess, Angie and Mari, are there any, last minute tips you have for applying fractography to trauma analysis?
Practice. I'm still doing a lot of it myself. Every time I break a coffee mug or a wine glass or whatever, I'm taking it to my microscope and trying to basically do a failure analysis. And really, I think the more you try it, even you can break some non-human bones, or if you have access to study human bones, just practice. Really, the more you start doing it, the more comfortable it'll become.
All right, thank you so much. Let's see, let me double check. Oh, we do have another question in the Q&A pod. Where can I find a list of cases where this science has been examined and accepted in a court of law?
I don't know the answer to that. Probably never in anthropology yet, but my guess is that this type of analysis is used frequently for other brittle materials, metals, ceramics, glasses. This is used in a lot of forensic examinations. So my guess is that there is precedent for this being admitted into testimony, but I'm not familiar with the cases.
Okay.
I do know that Frechette, who's one of the resources that we have listed, I believe, was somebody who was a pioneer in fractography of other materials and frequently testified in court. So that might be a place to look.
Great. Yeah, again, it doesn't look like we have any further questions in the Q&A pod. I mean, if there are no further questions, we can go ahead and wrap up today's webinar. Feel free to reach out to Dr. Christensen or Dr. Issa for any further questions, or if you want to dig deeper in some of the questions that were answered today, feel free to reach out. Thank you so much for attending, and thank you so much, Angie and Mari, for presenting today and being here with us.
Thanks for having us.
Thanks for having us, and thanks everyone for attending.
Thank you for attending today's webinar. As you depart, we kindly ask that you take a minute or two to complete our post-webinar survey. The link will be pasted in the chat and also appear as you exit the Zoom room. Your feedback helps us improve our webinars and continue providing the best experience possible. Lastly, we encourage you to check out our social media profiles, including Twitter, LinkedIn, and Facebook. You can find those links on the webinar page. There are also links to the Just Science Podcast SoundCloud and a link to subscribe to the FTCOE newsletter. Like, follow, or subscribe to stay up to date with everything the FTCOE is doing in support of the forensic community. Thank you again for attending, and we hope everyone has a great day.